So here we are. Let's go slideshow from beginning. And let's get a pen. So this is basically Laws of Motion Part 1. It's one chapter in your book, but it's probably, it's going to be 2 of our classes because it's long. And we're going to first of all talk about the conception of force. I remember sort of dreaming through this and then not really understanding insights about forces. So just stay with me for a little while on that. And then we're going to do Newton's laws. There's 3 of them. We're going to clear up a little bit of confusion about inertia and mass and weight because people tend to get those confused. Then we're going to apply all this stuff. And we're going to apply them to 2 types of situations, what we call equilibrium and non-equilibrium, which manifest themselves, which get presented as statics and dynamics. And if you want to be a mechanical engineer, you're certainly going to do a whole bunch of statics. And, you know, you've got a mechanical engineer, you're probably going to do a whole bunch of dynamics. I suspect more than mechanical engineers do statics. And it's one of those, like, gateway courses where it's famous. So get your principles down now. Concept of force. We tend to have a very colloquial way of thinking about the world because we live in a world and we talk about it. And unfortunately, we tend to talk about a complicated world. And sometimes we oversimplify it, and sometimes we make special cases, and sometimes, you know, we're just trying to talk about what we observe. Occasionally somebody comes along who can, like, step back, and Galileo was somebody who stepped back. Galileo was somebody who was able to get rid of friction from his experience of life. And that's an amazing feat. And when you get rid of friction, the universe gets a lot simpler. You can add it back in if you need it, but in principle, let's not think about friction. He was able to think about things affecting each other and the like. And that led on to Newton, and Newton really focused on forces and the action of forces. If I talk about forces, people will tend to divide them into 2 basic types. There's contact forces, so touching or pushing or pulling are 3 classic, you know, terms we use for contact forces. And then we have the kind of like the technical type forces, the sciencey type forces, like gravity to some extent, but magnetism and electrostatics. And if you go home and say, "Oh, I'm studying magnetism," people go, "Ooh," like that. "Oh, you're studying magnetism. You're doing, you know, this complex stuff." And it's a mysterious thing. You get this piece of metal that we call a magnet, and it can push or pull another magnet even though they're not touching. How do they even know each other exists? You know, I can't sit in a room and think and push you guys away by thinking about it. I've got to physically make contact with you. And yet magnetism can do that. Electrostatics can do that. So if I said to you, today we're going to study invisible force fields, you'd go, "Is this Star Trek? You know, is this like science fiction?" No, that's gravity is an invisible force field. Just we're very used to it. Magnetism, we're not so used to, but we're around it. Electrostatics, we see it when we don't want it. It's static cling, and it's the like. The ironic thing is that actually, when I touch my glasses, what is touching what? My atoms are made of electrons, protons, and neutrons, and my protons and neutrons are made out of quarks. So I can say my atoms are made out of electrons and quarks, and the electrons are on the outside and the quarks are stuffed in the middle. And if I get 2 electrons touching each other, that's a huge big deal because they don't want to touch each other. In fact, there's electrostatic forces, which means that the force field, the electrostatic field of my electrons interacts with the electrostatic field of the electrons of the glasses, and we have electrostatic forces that are in equilibrium. That's touching, you know. Nothing touches nothing. There's a very small gap where the electrostatic fields are. So they're all field forces, really. Just some are long-term and some are short-term. Some are long-distance, some are short-distance. But colloquially, it's useful to talk about contact forces and field forces. Let's take an example of gravity because we're most familiar with it. But let's try not to be on Earth. So let's think about the Earth and the Moon. Big Earth, little moon. Most of us were pushed around and pulled around by bullies or older brothers or parents, and it seemed like they had complete control over us and we did not have any control over them. So there's somehow this idea that the thing that's the biggest thing is not affected and the thing that's the littlest thing is totally affected. You know, my brother spins me around, he's not spun around, I'm spun around, you know. Absolutely not true. It turns out that my brother was affected on some measures exactly the same as I was affected. It didn't show as much because he had more mass. So we get these situations where we get interactions between objects that are not the same size, and it seems like one of them gets smattered and the other one doesn't. And so it seems completely unequal. But in fact, in terms of forces, it's equal. The classic example of that is you drive along in the summertime and you run into a love bug. The force of the love bug on your car is no bigger or smaller than the force of your car on the love bug. And yet the love bug is spattered. You don't have a car that's spattered against a love bug. The car's not even noticing it, and the love bug gets spattered. You don't kind of drive going, oh, 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 love bug, oh, oh, oh. You don't even notice they're there, and yet the love bugs are getting just, you know, their guts are basically spread all over the hood of your car. That is terminal for them. You don't even notice it. How can that be equal? And the difference is it's the same force, but that force on a truck makes absolutely no difference. It's negligible. But that force on that tiny love bug is catastrophic. So there is an equivalency, and it's the forces that are equivalent. We've got to keep reminding ourselves of that because we've got so many examples where that does not seem to be our experience. So here's the thing. Forces always occur between two pairs of objects. Hold on. You know, I am pushing on my glasses. Yeah, guess what? My glasses are pushing on me. And if the glasses don't push on me, I can't push on my glasses. There's always two objects. I push this chair. Yeah, but that's not that. It's not the same as that. When there's nothing pushing back, it's different than that. So the force I exert is because the chair pushes back and I push. It's a combination. When there's nothing to push against, I don't push. I move my arms, but I'm not pushing. Motion is not the same as force. Here's a motion. Here's the same motion. It'd be very different, won't it? I'm doing the same thing, but the forces are not the same. When I went to NC State, I had a boss that was problematic. And I had this Russian graduate student who would say, Tony, just reflect all the anger, reflect. And I'd go, man, this is really hard. And he'd say, you know, if you don't resist, he cannot push you. I'd go, that's all right for physics, but man, he can push me without me pushing back, I'll tell you that much. But it's true, you know. I made things worse because I didn't like what was going on, and two irresolvable forces. But they always come in pairs. So you can talk about a force in isolation, but there's another force that's with it. And sometimes the two forces on an object are not part of a pair. So here's my car. There's the thrust, if you like, of the wheels on the road. And there's the air resistance. And they are not part of the pair. They're part of two pairs. The way you can get it is the force of the road on the car with the force of the car on the road. And there's the force of the air on the car with the force of the car on the air. And you see how the pairs You take the two objects and you reverse them. So for here, the force of the road on the car is not a pair with the force of the air on the car. They're not part of the same action-reaction pair. Sometimes I only want to talk about those two. I don't want to talk about the action-reaction pair, but they're always part of an action-reaction pair. So for forces, you need two objects. You need them to be interacting. You get two forces, and the two forces are equal and opposite, even though, you know, in the vast majority of times, the two objects are not the same size. Force is a vector quantity. It's got a magnitude and a direction. If an object has several forces acting on it, the forces combine to give a net force. So if I have a pool ball, and I'm pulling on it, and my brother's pulling on it, and my sister's pulling on it, the pool ball doesn't feel that. The pool ball basically says, we'll add all these, when I add all these guys up, there's the force I feel, because this force is big, and that force is big, and this force is smaller. So I combine all those. It does not know if three forces are pulling on it or one force is pulling on it. It just sums the three to get the net force, and we call that net. Net force. When you get paid, if they tell you your salary, they tell you a gross salary. That's what you get before stoppages. When you get taxes taken out, that's your net salary. It's what's left over. It's the sum of all the positive bits and the negative bits, if you like. That's what we deal with. In many cases, we deal with the net force. So here's Newton's three laws. Galileo worked a lot of this, did a lot of the stuff about acceleration, and Newton came along 50 years later and basically codified things. Aristotle basically said the inevitable motion of a particle is rest, because there's no examples that you can see of particles that roll forever. It's nothing, you know. A stream rolls, but that water goes down to the ocean, it stops. You know, rain falls, but it stops. Inevitably, in the end, things stop. What about the moon? Oh, that's special. That's sacred. This is of mankind. This is corrupt. This is terrible. That's not of us. So the rules are different. They don't apply. That's what Aristotle would have said. It was really actually, to some extent, Galileo and then Newton who said, physics here is the same as the physics there. So we've got to be able to explain both of them using the same physics. So, what Newton came up with, and really from Galileo's work, was that if an object is rolling and there's no external forces acting on it, it will continue rolling the same direction with the same speed forever. So Newton's first law says an object that does not experience a net, meaning overall, external, meaning it's from the outside, you know, it's a pushing force or something like that, does not accelerate. Does not. Acceleration equals my change in velocity with time. So it does not speed up, it does not slow down, it does not go around a corner. Forever. So if I go into interplanetary space and I throw a backpack, I can come back in 1 billion years, and that backpack should be going at the same direction, at the same speed, unless another force has affected it. It went to the gravitational field of something or whatever. Doesn't cost any energy for that thing to keep rolling. It continuously costs us energy to move. But that's because we live in a friction-filled world. And we're going to ignore the friction and add it in when we need it. So think about space. Don't think so much about cars driving. Think often about space. And it just turns out if I start a motion, it doesn't cost me anything just to leave it and it will continue forever. That just seems like bizarre. The way we represent this is we say the sum of the forces equals 0, or sometimes people will say F net equals 0. The net is the sum of the forces. And sometimes people, you know, they go, the sum of F net equals 0. That's overkill. You don't need to put that down. But F equals 0 is a bit shorthand, and it's fine if you really know what the F stands for. But when we begin, I think it's really good to write down F net equals 0, or where did I put it down? The sum of the forces equals 0. Just emphasize, I'm talking about the overall force. Supposing it's not 0. Well, then we get a situation where here I have a big velocity and I have a backwards force. And we all know what happens when you have a backwards force. If I'm sliding into first base, I slow down. So that force causes that velocity to decrease. That change in velocity is an acceleration. So when I have a net force, I have an acceleration. It's not might have, it's must have. So I say the sum of the forces is equal to m times a. Force is a vector, mass is a vector, acceleration is a vector. Again, I could put down F net equals ma. You know, this means the same thing. Really, they're the same force. They're the same law, really. One of them's got a force and one of them's not got a force. So it's a bit pedantic to put them down as two laws, but everybody does. Everybody knows that the first law is called the law of inertia. And everyone knows the second law is not called the law of inertia. It's called Newton's second law. Newton had about 6 laws. This is his second one. Newton's third law basically says for every action force, there's an equal and opposite reaction force. If I push you, if I can push you, you must be pushing me. If you don't push back, I cannot push you. The ball being hit by the bat is the same force as the bat being hit by the ball. The love bug pushes my car with as much force as the car pushes the love bug. I pull on the sun with the same force that the sun pulls on me. Okay, let's try and distinguish a couple of things. Acceleration. Acceleration is a change in velocity. Velocity is speed and direction. So acceleration means a change in speed and or a change in direction. Either one will do it. Both will definitely do it. You can't have a change in speed which cancels out a change in direction. That's not possible. Either one will do it. Both of them together will do it. They can't cancel and get nothing out of it. So if you're going round a corner, you got an acceleration. If you're speeding up or slowing down, you've got an acceleration. If you're speeding up and slowing down while going round a corner, you've got an acceleration. If you have an acceleration, you must be speeding up and slowing down or going round a corner. You must be doing one of those three or two of those three or three of those three. Well, you can't do two of those three. But you can't speed up and slow down, but you know. You must be changing your speed and changing your direction or both. It's not could have, it must have. You must be. So when you see an acceleration, you know there's a change in speed and or a change in direction. When you see a change in speed and or direction, you know there must be an acceleration. When you know there's an acceleration, you know there must be a net force. If you know there's a net force, you know there must be a change in speed and or a change in direction because you know there must be an acceleration. So this linkage goes on forever. And if there's no net force, then there cannot be an acceleration, so you can't change your speed and you can't change your direction. So what I want you to get at is if you see that, you know that. Well, actually, in this case, you have to see both of them. But here, there's a change in speed. Oh, yeah, there must be a net force. There's a change in direction. Oh, yeah, there must be a net force. Link those three guys together. Link force with acceleration. Not. And break. It's not just a case of don't do it, but break it. Break force with motion. We link force with motion because for us, we need a force to overcome friction. But we're going to spend most of our time dealing in space. Then the other thing is just this idea about external force. I could have 10 forces acting on an object. You vectorially sum them. Baseball player hits a ball into the outfield. If the action force is the Earth's pull on the ball, the force of the Earth on the ball, what's the name for the reaction force? Anybody want to tell me? It's the force of the ball on the Earth. And how do you get that? You just reverse the order. Ball, Earth. It's the opposite of it. Yeah? So really, we shouldn't talk about pushing forces. We should talk about the force of my hand on the chair. The force of my palm on the table. Not my slapping force, not my pushing force, not weight. We should say the force of the Earth on the apple. But we're not. Certainly to begin with, it would be really useful. Eventually we're going to start talking about the force of the weight of the apple. But it's important at the beginning to really home in on this idea there's two objects involved. We should be able to name them. And then a plane is flying in a straight and level. So here's my plane. Flying straight and level. It is cruising. Cruising means with a constant speed. When you say cruising, you mean a constant speed. It is cruising with a constant speed of 150 miles an hour, 150 mph. Which is correct. The plane is experiencing a net force horizontally. The plane is experiencing a net force vertically. Both or neither. Now this is a plane. This is flying in the air. It's not in space. It's flying in the air. Okay. So decide. Decide for yourself. Say it's A, B, C, or D. No, just decide. We started at 11. Yeah, so we've got another 20 minutes. Okay. So decide. Turn around to the person next to you and like doing, that what is it? Rock, paper, scissors, go D and see if you agree. So if you've not got anybody next to you, pretend. So just compare notes with the person next to you. Think back about this thing about looking for the motion and inferring about acceleration and forces. Keep that visualization in mind. Think about the motion. The motion is the clue. Give you another minute and then we'll. And the answer is D. So why is it D?
No change in speed, no change in direction.
So first of all, go X and Y, yeah? Because we talk about two axes. And there's no change in speed horizontally. So there can't be a net force. Because if there's a net force, there must be an acceleration, which means a change in speed. So you know there's no force horizontally. No net force. Yeah, there's an engine, but there's also air resistance. So if there's no change in speed, there's no change in direction, there's no acceleration. And then vertically, the trick there is it says it's flying straight and level. Its vertical component of velocity is 0, and it stays 0, while ever it stays level. For it not to be 0 means it's climbing, or not to be 0 means it's falling. And it's not doing either one of those. Straight and level is just like nice and... So, no change in speed vertically means no acceleration vertically, means no net force vertically. So, no net force because no net acceleration, no net force because no acceleration. So basically, there's none of either, so the answer is D. Yep, agreed. Can you see how this is like visualizing, knowing really what the words stand for? What we don't do enough of, I think, is I'll find that people, they can do the math. The math is not so hard in this. They can do the math. I can show them the bits they need to know. By and large, they can do the math. And they'll learn the equations. It used to be when they had the equation sheets, they were just like looking at letters and guessing, and now we learn the equations. People learn the equations. Where they really get confused is they'll misinterpret what the letter stands for. So they'll know acceleration as a word, they'll have an idea about it, but don't really know what acceleration is. They've not really homed in on that because they're so busy looking at the tough problems that why waste time on the little stuff when there's that big mountain I've got to climb? But that's like, you know, I'm going to climb that mountain. Who cares about packing camping equipment? You know, I've got to get on with it. And so they arrive and they've not got any of the equipment they need to climb the mountain. And so my plea to you is don't think that those times that you spend not answering questions but doing physics are wasted. They're not. If you got hold of your conceptual physics book and reviewed the chapter that's similar to what we're doing before, that would be time well spent. Because it's kind of like that stuff that you've dealt with before. By revisiting, you'll get a keener understanding on it, and you'll make fewer misinterpretations. It's not the math that gets people; it's the interpretation, I think, that gets people in the end. Car is cruising at a constant speed of 50 miles per hour as it goes around a large circular track. Cruising, of course, means constant speed. Does it accelerate? And its choices are yes in the direction of travel, yes in the direction towards the middle of the circle, yes in the direction towards the center of the track, away from the center of the track, and then no, it is not accelerating. So again, decide for yourself. And then compare.
Oh, wait.
It's a constant speed, it's not accelerating. Makes no sense, but you gotta know that.
But if you like this, right? It's like this, it's going around the track. It's going this way, it's accelerating. It's going this way, it's accelerating. It's like that, you know what I'm saying? But I could be wrong, I don't know.
I want a donut.
I don't know why I'm making
I think it has something to do with the original equations of acceleration, like it has something to do with direction. Oh no.
Wait.
So what do you think? The correct answer is it's going to be B. Yeah. Now, first of all, yes. That's half the battle. Yes. You picked an answer that was yes. So clearly the answer is not no, because it is changing direction. Agreed? So that one clearly is not right. And then the question is, which way is the acceleration? I'm cheating a little bit because you've not actually done circular motion with me yet, but if you think about it, you can think about it in several ways. If that's my initial velocity, and that's my final velocity, like from there to there. What kind of acceleration do I need to get that to happen? I've got to, in x and y components, so I've got to start giving it a bit of vertical component, so I need an acceleration that goes like that. Certainly not like that. That A would be all wrong. You'd start going like that direction. So my A must be there, and that's pointing towards the middle of the track. It's a little bit hand-waving. Reason why sometimes people, if it was the first one, you would just speed up going, you'd basically plow into the corner, which you sometimes see. My brother-in-law is a truck, my brother-in-law is an interesting guy. He does two things. He does transmissions, and he does long-distance truck driving at different phases of his life. And he said, and the reason is when the economy is doing great, trucking goes through the roof. So there's a lot of money to be made from it. And when the economy is not doing so well, people hold on to their old cars. So transmissions go through the roof. They don't trade a car in. So either way is all right. And he was telling me, he goes, you know when you're going on one of those curly kind of like slip roads to get off the interstate or something, and it goes 50, and you know you're flying around it like 60 and stuff like that. He goes, that's not for you. That's for me. He goes, if I'm in an 18-wheeler and I'm doing more than 50 miles an hour when I get onto that slip road, when it says 50, I will go off the end. He goes, for us it's like the critical speed. You must be below. There's no way around it. For cars, yeah, you can cheat a bit and go a bit faster. But for us, we can't. And you see that occasionally people just miss the turn. And the acceleration for them, they might be braking, whatever. But if they were to do this, they'd do that. So then it's either outwards or inwards. And for this argument over here, I'd argue that you can tell it should be inwards. This is called centripetal, petal acceleration. And there's this thing out here that we sometimes call centrifugal. And you might have heard of centrifugal. How many people have heard of centrifugal? How many people have heard of centripetal? Yeah, about the same, a few less perhaps. Centrifugal is a fictitious thing. I don't like to talk about centrifugal. It's not. It's real, but it's like real that a dream's real, but you can't put it in a bottle. It's kind of real like that. It's something you can talk about, but I can't point to it and say there's a centrifugal force. I can point to a centripetal force, say there's a centripetal force. So okay, let's do some numbers with this. So, does this object accelerate? And if so, in which direction? And what is the acceleration? So the trick is divide it into horizontal and vertical, and ask yourself, you got two equations, the sum of the forces equals 0, or the sum of the forces equals ma, and I want to know, does it accelerate? Mass is not 0, mass is 1, so there must be a 1 in there. So you're looking for when forces cancel each other out. So you can look at the pairs of forces and you can compare them. But only consider opposite pairs. And then get an answer and then talk to your neighbour and see if you're good. I'm going to look just briefly ahead.
Vertical force, same 0, to go 2 same direction.
So these cancel.
Yeah, not bad, okay.
Well, you subtract it, and then your force is 2 newtons, and then your MA mass is 1 kilogram, and then do the math for your acceleration. You just have this to be the same.
So,
Your force equals your acceleration. So we subtracted the 5 and the 4 to get your net force, so
That's F equals in that. So let's do it, we'll hit, you cancel it out first, so 2 equals 1. And think about how 1 equals 10.
okay, let's have a look at this. So I'm going to say the sum of the forces vertically equals. I'm going to go plus 2, that's the green one, added to minus 2, that's the brown one, equals 0 Newton. So the A vertical equals 0 because the sum of the forces vertical equals MA, which equals 0. So A must equal 0. Agreed for that one? Then I'm going to say the sum of the forces horizontal is equal to plus 5 added to minus 2 minus 3. Minus because it's pointing towards the left, which equals MA. So I'm going to say plus 5 added to minus 3 is equal to 1 times A, because the acceleration, because the mass is 1. So that's going to be plus 2 is equal to A. So A is equal to plus 2 meters per second squared. So it's going to be, yes, to the right, that's positive, at 2 meters per second squared. So I used my relationship and I applied it vertically and I applied it horizontally. If there had been a force like here, I would have taken the horizontal component of that force when I did the horizontal bits, and I would have taken the vertical component of that force when I did the vertical bits. Can you see how components become like breathing? They're just like, you cannot afford to not be able to do components. It will just eat your grade away. So you've got to be, if you cannot do components, you've got to come and see me, or you've got to go and see somebody, or else, you know, you could be Albert Einstein, but it's going to eat your grade away. It's going to be a thing that you've absolutely got to know. If a student pushes on a wall, action force with 10 newtons, so there's my 10 newtons. With what fall does the force push back? The wall pushes on the student with what force? There's some nice language for you, man. So that's going to be minus 10 newtons. And it says, you know, with what force? It's a magnitude, so it's 10 newtons, yeah. Oh, I've got 7 minutes for this. Oh, normally a car pushes on the road, action force with 100 newtons. And the road pushes back, reaction force with 100 newtons. That's what gets me going in the morning, yeah? I push on the road pushes back. On an icy day, can the car tyre push on the road with 100 newtons? I put my foot on the gas, I'm doing everything I'm supposed to do, the car's doing everything it's supposed to do. Do we get the same outcome from the car? Does the car push on the road with 100 newtons?
With ice in between?
Pardon?
With the ice in between?
With the ice, when it's on ice? No. Hold on. I'm doing everything I normally do. How come when there's no ice there, I do push on the road with 100 newtons, but when there's ice there, I do not push? I'm doing everything the same, but I'm getting a different outcome. And it's like, yeah, thump the air and thump the wall. It's a completely different outcome. Because the force is an interaction. It's not a thing. It's an interaction. You know? If there's no ice cream to eat, you cannot have that ice cream headache. You know, you need your headache, and you need the head, and you need the ice cream. It's like, you can't just have, you know, man, I got the head, but I'm not eating ice cream. Okay, well, you're not going to get an ice cream headache. The force is an interaction. It's not a thing in its own right, to some extent. Pickup truck. Pushes on a car with a constant 50 miles per hour along a straight and steady level of I-275. Compare the force of the pickup on the car with the force of the car on the pickup. So which is bigger, which is smaller? Are they both the same? Three choices. The force of the pickup, the truck, on the car is less than the force of the car when they're going down the road. You've seen them. Somebody broke down, the person comes behind and just pushes them. Yeah, they're touching like that. You've seen that. It's probably illegal, but you know, they just push them out of the way. Constant speed. Force of the pickup on the car is less than. Force of the pickup on the car is more than. Is equal to. Force of the pickup on the car is more than. We got 6 minutes, so I'm going to give you I'm going to give you 1 minute to quickly decide and discuss it with your neighbour. Okay? Which is it?
But it says,
So, I'm going to tell you the answer. I want someone to justify it for me. The answer is that they are equal. What's the justification? No acceleration. Okay. Fair enough. Okay. Pickup on the car accelerates a car from 0 to 50. So here we have the same pickup. And here we have the car. But there is an acceleration. On a straight and level section of 275. Same question. Now that there is an acceleration. Think about it, talk to your friends. Is it the same answer? Before there was no acceleration. It was coasting at 50. Now you're getting that thing going. You're starting it off. Are the two forces equal now? And the answer is... The answer is that they are the same. Hold on. There's acceleration this time. They cannot be the same. The sum of the forces equals ma. If the sum of the forces is 0, A must be 0. This makes no sense, but it does make sense. And it comes down to my diagram. There's the force of the pickup on the car, and here's the force of the car on the pickup. And the force of the pickup on the car is equal to, those two are equal. But the sum of the forces equals ma. Oh yeah, it's the sum of the external forces, not internal forces. These are both internal forces. The external forces, well, we have the force of the car on the air. We have the force of the air on the car. We have the force of the road on the pickup. And we have the force of the pickup on the road. There's three sets of action-reaction pairs. And we were comparing those two. And under all circumstances, an action-reaction pair are equal and opposite because they're an action-reaction pair. What determines whether we accelerate are these external forces, and there's one external force and there's the other external force. So if the force of the pickup on the road, or the road on the pickup, is bigger than the force of the air on the car, then you speed up. If the force of the pickup of the road on the pickup is equal to the force of the air on the car, then you coast. And if the force of the road on the pickup is less than the force of the air on the car, you slow down. So it's not any old force equals ma. It's the two, it's in this case the two net external forces equals ma. And the way you speed up is you make this force or this force bigger than that force, and the way you slow down is you change those back again. So we've got to distinguish between net external forces and internal forces. I can give you give me 1 minute, I'll give you one last example of that. My car is broken down, I want to push it off the road. I open the passenger door, and I lean in, and I push on the steering wheel, and I push, okay? My car is stationary. What happens to my car's motion as I push? Assuming it's a small car and I'm strong, what happens? It speeds up, doesn't it? It accelerates towards the pavement and I steer it, yeah? So when you apply a force to that dashboard or steering wheel, that causes the acceleration, yeah? Okay? Well, I get tired, so I just sit in my seat and now I push on the dashboard. Will I accelerate? Same force. I'm pushing just as well. My feet are not on the ground, but same force. This is an internal force. The action-reaction pair. One end is on the steering wheel and the other end is through my butt on the seat. It's all inside the car. When I'm stood outside, one end's on the steering wheel, the other one is on the road going, towards Kansas. It's like they're very different things. And so although we will talk about individual forces, always try to remember what's the action-reaction pair. Get used to picking out the external forces and not worrying about the internal forces. I'll see you guys next time. That was a good session, I think.